30. Which structure below is a dipeptide? For this problem, it's probably a good idea to understand what a peptide is. And a peptide is basically a chain of amino acids. So a dipeptide, di meaning two, would be a peptide that consists of two amino acids. So it's probably a good idea to draw out what an amino acid looks like. And if you remember, an amino acid will have a carboxylic acid group and side chain and an amino group, like sort of like this. So if we're labeling these, this is the amino group, this is the side chain, and this is the carboxylic acid. Okay, so whenever we link amino acids together, we're going to have a dehydration reaction taking place, which means we're losing a water molecule. And the way that we do this is we take this OH from this carboxylic acid and we take one of the hydrogens from another amino acid, another amino acid's amino group, and we kind of like merge them together. And then so these two parts of these functional groups is going to make up the water molecule that we get rid of. So when we put these together into two amino acids, I'm going to draw this over here. We're going to get something like this, where we have one amino acid, and then instead of having this OH group at the carboxylic acid position, we're going to have this peptide bond to another amino acid. So it's going to look like this. And keep in mind, this is the other amino acid's amino group, but instead of having two hydrogens bonded to this nitrogen, we only have one, since the other one was we got rid of it when we went through the dehydration reaction. And to complete this picture, it's going to just look like this. And we just kind of have to see which one of these choices looks the most like what we drew over here. So it doesn't look like A, it doesn't look like C, and it doesn't look like D. The reason why is because I guess the way I saw it is we have these two bonds or these two other groups between these carbonyl groups. So we just count that. So there's only one here in A. There's 1, 2 in B. There's only 1 in C, and there's 1, 2, 3 in D. So since we have these two in the structure that we drew, it has to be B. So this answer is B. 31. Which of the following amino acids is most likely to be found on the outside of a protein that is in an aqueous environment? So we're given these 5 different amino acids, and we're told that this protein is in an aqueous environment. Aqueous meaning an environment with water. So I'm just going to write that. And remember that water is polar. So basically, we just need to find the most polar amino acid because like mixes with like in this case. So to do that, let's look at the functional groups of each of these amino acids. So we always have an amino group and a carboxylic acid, so we don't really care too much about these because they're going to stay consistent throughout all of these amino acids because all amino acids have those groups. So what we're looking at mostly is just the side chains, which are these. And as we can see, alanine has just a methyl group or CH3 on its side chain. Leucine has this sort of branched alkane in its side chain. Phenylalanine has this aromatic ring in its side chain, and serine has a CH2 and an OH group, and valine has a slightly less branched alkane side chain. So in this case, the most polar side chain will be the one that serine has because we have this OH group, and an alcohol group, which is an OH group, is pretty polar. And it kind of looks similar to water because, it has an oxygen and a hydrogen. So that's a good hint to its polarity. So the answer to this question will be serine, which is E. 32. The vapor pressure of 1 propanol is 10.0 torr at 14.7 degrees Celsius. Calculate the normal boiling point of 1 propanol given that the heat of vaporization of 1 propanol is 47.2 kilojoules per mole. So for this problem, we're going to want to use this equation, which is given in your equation sheet. And the reason for that is because we're given the pressure or the vapor pressure at one temperature, which is this, and the temperature is this. So that's going to be our P1 and T1. And we're also given the heat of vaporization, which is this delta H vap. And we're also given the normal boiling point, which is going to be basically the temperature T2 at P2 equals 1 atmosphere of pressure. So whenever we see something asking for the normal boiling point, it means that the pressure, or P2, is going to be 1 atmosphere. And now we can kind of just plug in what we know. So we know that P1 is going to be 10.0 torr, and so we can write that down. But as we can see, this R constant that we have to plug in to this equation here is in a different set of units. It's J over mole times K. So we have to convert this 10.0 torr to whatever it's going to cancel out with this with the units of the other parts of the equation, namely R. So there's a handy conversion rate that's given to you on your equation sheet, where it says that 1 atmosphere of pressure is equivalent to 760 torr. So we can just do a simple dimensional analysis, and we will get P1 is equal to approximately 0.01315,789 atmospheres. And we're also given that T1 temperature is 14.7 degrees Celsius. So T1 equals 14.7 degrees Celsius. But remember that, like we did with the previous part for P1, we have to convert the units so that they would cancel with R. And in this case, we see that there's a temperature unit with kelvins. So we need to convert this temperature 1 to kelvins. And to do so, we just have to add 273.15, and we're going to get 287.85 kelvins. And as I stated before, P2 will just be 1 atmosphere of pressure because we're looking for the normal boiling point. And we're given HVAP. HVAP is this, 47.2 kilojoules per mole. But since we're working with joules and not kilojoules, as you can see in R, the units are in joules. We just have to multiply this by 1,000. So we're going to get the same thing as 47,200 joules per mole. So this is our delta HVAP. And so now we are ready to plug in everything to our equation and solve for T2, which is our normal boiling point, or the temperature, which is our normal boiling point. So substituting in all of these values, we get ln of 1 atmosphere over 0.01315,789 atmospheres. The atmospheres cancel out, so we're just left with ln of a number divided by a number, and this is equal to negative 47,200 joules per mole over our R constant, which is 8.314 J over mole times K. And this is all multiplied by 1 over T2, which is our unknown, minus 1 over T1, which we previously established is 287.85 kelvins. So if we simplify this a little bit, all of these units will cancel out eventually, and we're going to get this is equal to approximately 4.3307. This will be approximately equal to negative 5,677.171, and then we're going to bring down this parentheses term over here. And actually 1 over 287.85 is approximately 0.003474. And we can distribute this negative 5,000 number to both of these terms in the parentheses, and we'll get something like this. Plus 19.7225. And we can subtract 19.7225 from both sides, and this will give us negative 15.3918 is equal to negative 5,677.171 over T2. Cancel out the negatives, and we're left with this sort of ratio thing. We can cross multiply, and when we cross multiply, we get negative we cancel out the negatives, so just 15.3918 T2 is equal to 5,677.171. Divide both sides by 15.3918, and T2 will be equal to approximately 368.8 kelvins. So you might think this is our final answer, but all of these answers that were given as answer choices are listed in Celsius, not in kelvins. So we need to do one more conversion, and to do that, we just subtract 273.15 degrees Kelvin from this T2 that we found, which is in kelvins. And this will give us our answer in Celsius. It's basically just the opposite of what we first did when we converted T1 from 14 degrees or 14.7 degrees Celsius to 287.85 kelvins. We're just doing the opposite of that. So when you do this subtraction, you'll get approximately 95.65 degrees Celsius, and this is approximately equal to 96 degrees Celsius, and that's going to give us our answer D. Which of the following best describes the properties of a 1 molar solution of NaCl in water? So in this question, we're given this table of normal boiling point, freezing point, and electrical conductivity. And essentially, it's just asking us what's going to happen to the properties, these properties of boiling point, freezing point, and conductivity. Is going to happen to this solution when we add table salt or NaCl into the water. So we first need to note that NaCl is an ionic compound, and that's important because it means it dissociates freely into Na plus and Cl minus ions. And these are going to be kind of just swimming around in the water. So the first thing we need to look at is the conductivity, which is probably the most obvious part. Since we have free ions and they carry charge and they're just freely moving around in the solution or in the water, this solution will be conductive. So we can immediately eliminate C and E as these cannot be our answers. Second, we can look at the normal boiling point. And to do this, we should probably draw sort of like a diagram. So when NaCl dissolves in water, it dissociates into these free moving Na plus and Cl minus ions. And so before it dissolves in the water, this sort of, if you take a cross section of like a flask with the water in it, before you put the NaCl in it, it's all water. So the surface of the water is all water. But then after, once you have these dissolved ions in the mix, you have sort of these ions as well as the water, but it's not 100% water on the surface. And that's important because now that we have fewer water molecules than before on the surface of the water or on the solution, it's going to be harder for the water to escape, or it's going to take longer for it to escape and vaporize. This means that it's going to have reduced vapor pressure, and in turn, the boiling point of this solution will increase. So normally, the boiling point of water is 100 degrees Celsius, so we're just looking for answers with greater than 100 degrees Celsius as our normal boiling point. And we can see that both B and D have this, but A does not, because A says less than 100 degrees Celsius, so A cannot be the answer. So the final thing we have to look at to differentiate between answer choices B and D are the freezing point. So in B, the freezing point is seen as less than 0 degrees Celsius, and for D, it says greater than 0 degrees Celsius. And this is very similar to the logic we applied for the boiling point, but kind of in the opposite direction. So we know that whenever things freeze, like especially water, when it freezes, it forms a crystal lattice. And this lattice has a pattern. So normally, if we just have all water molecules, the lattice doesn't really have issues forming. It'll just form because the pattern is not disrupted because it's all just water molecules. But when we add these Na plus and Cl minus ions into the mix, it's going to be disrupted. The lattice is going to make it harder for the lattice to form in the proper pattern. So it's kind of like, imagine if someone keeps getting into your way and you're trying to do your homework, but like, let's say your roommate keeps asking you questions like, oh, do you take out the trash today? Did you do this? Like, can you do this? And it makes it harder for you to finish your homework on time or as fast as you could if there weren't any distractions. So that's kind of like what's happening with the freezing point. So because there are these ions getting in the way from the NaCl, it's going to be harder to form the lattice, and therefore it's going to make the freezing point lower. It's going to decrease the freezing point, meaning it is going to be harder to freeze or it takes longer to freeze. So in this case, since water's freezing point is normally 0 degrees Celsius, it'll just be less than 0 degrees Celsius. So we see that B is our answer. 34. An aqueous solution is 45.0% by mass sucrose and has a density of 1.203 grams per milliliter. The molality of sucrose in this solution is one of these. For this problem, it's a good idea to kind of differentiate between molarity and molality because sometimes it's easy to get confused by these terms. But molarity, as we have probably learned before, is denoted with a capital M, and it's moles of solute divided by liters of solution. And in contrast, molality with an L is denoted by a lowercase m, and it's going to be the moles of solute over the kilograms of solution. And I want to say solute and solution here kind of loosely because whenever we're measuring mass, it's kind of like it doesn't have to be a solution. It doesn't have to be a liquid or an aqueous solution. For example, if you're asked about the concentration of like copper in a metal block that has like copper and some other metals in it mixed together, you're more likely to want to know the molality than the molarity because it's easier to measure the kilograms of the quote unquote solution or the overall metal block in kilograms rather than liters. So that's why I don't say solution as in like it's definitively has to be a solution. It could just be like a solid or anything like that as well. But in this case, we're dealing with a solution because we are told that this is an aqueous solution. And in this case, we are told that the aqueous solution is 45.0% by mass sucrose. And that means that if we have 45% mass sucrose, if we take a 100 gram solution, this means we have 45 grams of sucrose, and 100 minus 45 is 55 grams of solution. And this means that 55 divided by 1,000 is going to give us our kilograms of solution that we want here. And that's going to be 0.0550 kilograms. And then we also have to find the moles of the solute. In this case, the solute is sucrose. I'm not going to bore you with the calculation for this, so I'm just going to give you the molar mass, which is 342.3 grams per mole. You can find this by Googling it up or whatever, but on the exam, you're going to have to calculate it yourself, I'm pretty sure. But as you can see, you don't have to memorize anything since you're given the periodic table and you're also given the chemical formula for sucrose. It's just a very tedious sort of calculation, so I'm skipping over that. Anyways, we know that this is the molar mass of sucrose. So to find the number of moles, we just take the this 45 grams in this hypothetical scenario of 100 grams total solution, and we divide that by the molar mass. So 45 grams times 1 mole over 342.3 grams, which is the same as just dividing it, but it might be helpful to write it out as a dimensional analysis problem to cancel these things out, these units. We're going to get around 0.1315 moles of sucrose. So now we have our two crucial quantities that we need. We need this number of moles of the solute or the sucrose, and we need the kilograms of solution. So now we just kind of divide them. So 0.1315 moles divided by 0.0550 kilograms should give you around 2.39 with the lowercase m for molality. And that's going to match up with answer choice C. So this the answer to this question is C. 35. Which of the following aqueous solutions has the highest boiling point? When we're considering the highest boiling point between a number of substances that we're given to choose from, there are two major considerations. The first one, and the more important one, is the intermolecular forces. So that means that ionic bonds and then polar covalent, or technically hydrogen bonds, and then polar covalent, and then non-polar covalent. So in this case, ionic would have the highest boiling point because it's the strongest type of bond, so it's the hardest to break, which means it will have the higher boiling point. On the other end of the spectrum, non-polar covalent bonds don't have a lot of attraction to each other, so the atoms are they don't have a net dipole moment, so they're not very attracted to each other as much, so then it's easier to break those bonds and they would have a lower boiling point. The second thing we need to consider is the mass. So that's where these numbers 1.0, 0.75, 0.75, and 2.0 moles comes into play. So basically, it's a process of elimination game. We can first look for the intermolecular forces, and then mass can be sort of our tiebreaker in this case, probably. So let's go down to the list and see. So for A, we have LiNO3. We know that Li is a metal, and NO3 is a group of nonmetals, but since it's not just one nonmetal, this has both ionic and covalent bonds. We don't know yet if this is polar or nonpolar covalent, but we know that it is covalent, and we also know that there is an ionic bond in this molecule. For the second molecule B is KCl. We just have an ionic bond in this case because Cl is a Cl is a nonmetal, right? But it's not ionic and covalent because we only have one nonmetal atom. If it was multiple nonmetal atoms, then that would be sort of like its own covalent bonding, and then on top of that, there would also be the ionic bonding to the potassium or the K atom here. So this one is just ionic. For C, CuCl2, this is going to be the same as A. It's going to be ionic and covalent because we have this copper, which is a metal, so that signifies that it has an ionic bond. And we also have two chlorine atoms. And because we have more than one nonmetal atom, that must mean that there is some sort of covalent bonding as well. For D, we have glucose. Glucose, all of these are nonmetals, so this is just going to be covalent. And for pure water, H2O, the same thing. It's all nonmetals, so this is just going to be covalent. So right off the bat, we know that in terms of intermolecular forces, the more of these forces there are, and the higher they are on this hierarchy that we just wrote out, the greater or the higher the boiling point will be. So if we look at this, we know that pure water and glucose will have the lowest boiling points because they are just covalent. And we see that covalent is below ionic in this sort of order we listed out. Next, we have this choice B, which is only ionic, and that's going to be an intermediate boiling point. It's not going to be the lowest, as in pure water or glucose, but it's not going to be the highest because it doesn't have additional covalent bonds that would make it even harder to break. Because keep in mind that more bonds, more types of bonds overall would just be harder to break, and then they would contribute to a higher boiling point. So it's not B. So the question is basically between A and C now. And to figure out if these are polar or nonpolar covalent bonds, we can draw Lewis structures. So for NO3, for example, this covalent or the nonmetal component of this molecule, we know that NO3 minus, because this will dissociate into Li plus and NO3 minus. We know that nitrogen has 5 valence electrons and oxygen has 6. So 3 oxygens times 6 valence electrons each plus 1, because we have this -1 charge. That's going to give us 24 valence electrons total. And we kind of should be able to see that the middle atom is going to be nitrogen because we have 1 nitrogen and we have 3 oxygens. So that's pretty intuitive. And we can start by drawing a very simple Lewis structure here. And I'm going to move this down a little. And keep in mind that with Lewis structures, you want to start filling out the octets of the atoms around the central atom and then evaluate the formal charge and if there's any missing charges, and then only then will you add stuff to the central atom. So in this case, to form an octet for all of these oxygens, we just add 3 lone pairs on each. And in this case, since oxygen has 6 valence electrons, and then this is 2, 4, 6 valence electrons, and then there's this 1 electron here, or just 1 bond, because technically this bond has 2, but it's just counted as 1. 6 minus 1 equals, that is -1. So that means that each of these oxygens has a formal charge of -1. Now on the other side, nitrogen has 5 valence electrons, and we see no lone pairs, and we see 3 bonds. So this is going to have a +2 charge. And 2 plus 2, it's the same thing. So we know that we have these -3 charges plus 2. That's equal to -1 net charge, and that checks out with what we have here. So that's a good sign. However, there is a more stable way we can draw this Lewis structure. Because keep in mind that the most stable Lewis structure, or the preferred Lewis structure, is going to first have the lowest amount of formal charges possible, and secondly, they want the most electronegative atom to bear the negative charge. So in this case, oxygen is more electronegative than nitrogen, and it has a negative charge, so there's nothing we need to do about that. However, we can reduce one of these formal charges to be 0 by changing one of these lone pairs into a delocalized sort of electrons, or basically change it into a double bond. So if we do this, we will get something like this, where these 2 oxygens on the bottom still have a -1 charge, but this oxygen here has been neutralized because now it has 2 bonds and it has an octet, and its formal charge is 0. Now in this case, nitrogen is going to have 5 minus 4 minus 0, or 5 minus 0 minus 4, because it has no lone pairs, but it has 1, 2, 3, 4 bonds, and that's going to be a 1+ charge. So still overall, they do balance because we see 2 negative charges and 1 positive charge. So this is going to be our Lewis structure for NO3 minus. And as you can see, molecular geometry depends on the central atom. And because this nitrogen atom doesn't have any lone pairs, there's not going to be any repulsion effect So all of these groups are going to they're going to all be equidistant, or the bond angle is going to be the same. It's going to be around 120 degrees, I think. And because of that, the dipole moments of each of these oxygen-nitrogen bonds is going to be canceled out. So this is going to be a nonpolar covalent molecule. Now, let's move this over here. In the case of CuCl2, we could draw the Lewis structure to confirm it, but we don't really have to, because we see that this covalent part of this, or like the non-metal part of this molecule, is completely made up of the same atoms. It's just two chlorine atoms. And anything that is only made up with of the same type of atom is going to be nonpolar covalent, because they're the same types of atoms, so there's not going to be any difference in electronegativity and stuff like that. So there's not going to be any net dipole moment. So this one is also going to be nonpolar. So I'm going to write that down. And now, since both A and C are ionic, covalent, and nonpolar, we can't just use IMF, or intermolecular forces, to determine which one of these has the highest boiling point. So now we have to look at the mass. So that's where this 0.75 and 1.0 moles comes into play. I'm not going to bore you with the molar mass of these compounds, so I'm just going to give them to you. But I think on an exam, you'll have to calculate it yourself, but that should be pretty straightforward. But anyway, a quick Google search shows me that the molecular mass of LiNO3 is about 68.95 grams per mole. And for CuCl2, it's about 134.45 grams per mole. So we can't do things in moles because it's not really an accurate comparison. So we have to convert both of these into grams to figure out which one has the higher mass. And the reason why the compound with the higher mass, or the higher mass, has the higher boiling point is because the greater the mass, it means there's more interactions between molecules, because there's just more molecules, right? Because if there's more mass, there's more molecules. And that would mean that these interactions would overall just be harder to break, or there's more of them to break, so therefore it would be harder to break, and then that would lead to a higher boiling point. So this is a simple dimensional analysis problem from here on out. So let's take 1.0 moles of LiNO3 times 68.95 grams per mole of it. This will cancel, and we're going to get just 68.95 grams of LiNO3, because 1 times whatever is just that. And for CuCl2, we have 0.75 moles of it multiplied by 134.45 grams over 1 mole. The moles cancel, and we are left with about 100.8375 grams of CuCl2. This is obviously greater than 68.95 grams, so in this case, our answer is C. The 0.75 moles of CuCl2 is going to be the aqueous solution with the highest boiling point. 36. In the phase diagram shown below, what is the most stable phase or phases at point A? So this question is pretty conceptual, but basically in a phase diagram like this, we're going to have something like this and a critical point here. And basically, as pressure goes up, temperature goes up, this part will be the solid, this part will be the gas, this part will be liquid, and this part will be the supercritical fluid. Sorry, my handwriting is not great. But anyways, as you can see here, A is pretty comfortably sitting in the liquid position, so this answer will be C, liquid. If it was liquid vapor equilibrium, it would be somewhere along this line, because as you can see, this line is where the liquid and the gas sort of overlap or intersect, and we don't see that. And we also don't see A being somewhere like here, which would indicate something like a supercritical fluid. And obviously it can't be solid or gas, so yeah, it's liquid.